Hello everybody, I hope you're all doing well. So we're going to solve a problem on work energy principles as applied to particles. Okay, so here is a problem setup. So to begin with, I have some kind of an inclined surface that leads on to a horizontal surface. Okay, so here is the inclined portion and here is the horizontal portion which I'm going to complete. At the end of this, there is a fixed wall here, and of course all of these surfaces are also fixed surfaces, which means that I can put my typical hatch marks on this surface. And this problem, it has a lot of resemblance to what you might see on the unloading dock of maybe grocery stores, and in terms of unloading vestibules and so on. Okay, and you're going to see that significance now there is a spring here, okay, which is at the end of this wall, at the fixed wall. Okay, so one end of the spring is connected to the fixed wall here. Okay, and the other end of the spring is connected to some kind of a cushion element, okay, which is of not much consequence to us. It is just to show that, okay, if a packet or if a particle comes and sits and hits the spring, it is not going to get unduly damaged or anything. Okay, so that's essentially what it means. Okay, now this spring has a stiffness K, so that's given to us. The value, I'll be writing it down in a minute. And then we also know that the unstretched length of this spring is given to us. I'm going to label that as L naught. Okay, and we will specify the values in a minute. Okay, so this is going to be the unstretched length of the spring, L naught, and let me draw this as a dotted line. Okay, so what's happening is this. There is a small box that is starting its travels right at the top here. Okay, so there is this box here, and there is somebody who's giving this box a gentle nudge. Okay, which means that this box is going to have a certain initial velocity as it starts from the top of this surface. So let's say that this point, I'm going to call it as point 1. Okay, so this is where the box starts. Then let me call this as position 2. Okay, and I'm told that the incline here has an angle of 30 degrees with respect to the horizontal. Okay, and then this box is given a little gentle nudge, which means that it's kicked with a certain initial velocity here, and this is the direction of that velocity. The magnitude of this velocity is given to me as 1.12 meters per second. Okay, and the mass of this box is also known to me. Okay, this is going to be 2 kilograms. Okay, so the mass of the box is given to me. L naught is 0.8 meters. Okay, and then the stiffness of the spring is also given to me. The stiffness of the spring is 20 newtons per meter. So let me see if I can write that out here. Okay, so this is going to be 20 newtons per meter. Okay, so this is the stiffness of the spring. So what am I supposed to do in this problem? I'm told that this box is going to travel starting from the point 1. It's going to plop down onto the incline because it has an initial velocity, and then it's going to gain some energy, right? Because it is dropping down from a certain height, which means that it's going to gain some speed as well. When it's going to come to point 2, depending on how friction is acting, and then it's going to start going along the horizontal track here, and then it's going to hit on this spring element, okay, which is going to prevent this box from completely getting damaged as it hits the wall or something, and by means of this cushion. And essentially this acts as something that will stop the motion of the box if the spring is very stiff. Okay, so what are we supposed to do in this problem? Here is what we're supposed to do. So if the coefficient of friction, okay, if mu k is equal to 0.15, and so I'm going to write 2 mu k's. Okay, so mu k is 0.3. So this is between the box and the inclined surface, and this is between the box and the horizontal surface. Okay, this is the inclined surface. Okay, and if you are told that the total length of this inclined surface is 3 meters, okay, so I'm told that this length is going to be 3 meters along the hypotenuse. Let me write the 3 better. So this is 3 meters here, and then I'm told that the total length of this horizontal portion is also 3 meters. So let me mark that distance right here. So this distance starting from here all the way to the end here to the fixed wall is given to me as 3 meters. Okay, so if that is also given to me as 3 meters, and let me draw this as a dotted line here because it's a dimension. Okay, so if these are known to me, if the coefficient of friction is known to me, then determine the maximum compression of the spring, maximum compression of the spring, okay, as the box is cushioned by the spring, as the box is cushioned by the spring upon impact. Okay, so this is typically what we are asked to find out, and also let us also find out the length of the spring, okay, at that instant. Okay, so these are the things that we need to find in this problem. Okay, so determine, what do we need to determine? The maximum compression of the spring. Okay, at what position? This is when the box comes and impacts upon the spring as it slides down and travels along the horizontal surface, and also find the length of the spring at that instant. Okay, which means that when the spring is compressed to its maximum position, then what is the total length of the spring? Obviously that length is going to be lesser than the initial length. Okay, so L naught here, and let me just very briefly write it out. So this L naught here, this is called the unstretched length. Okay, and so we know the mass of the box. This is the velocity, this is the initial velocity. Okay, so this is initial velocity at position 1. Okay, so this is the information that is given to us. So I have a box which is traveling down this ramp. The coefficient of friction is given to me here between the box and the incline is 0.15, and then here between the horizontal surface and the box is going to be 0.3. So slightly more rougher here and not as rough on the incline. Okay, what am I supposed to find out? I'm supposed to find out the maximum compression of the spring and also the length of the spring at that instant. Okay, and the basic idea is that I'm going to use the work energy theorem for this particular problem. Okay, so I'm going to use, so we shall solve using work energy principles. Okay, one thing to keep in mind is because of the fact that there is kinetic friction here, energy is not conserved. Okay, so due to friction being present, okay, energy is not conserved. That is something that is quite obviously seen in this problem. Okay, so here is what I'm going to do. I'm going to draw the problem 2 times. Okay, I'm going to draw the position of the box at when it is at the start. Okay, and then I'm going to draw the position of the box as it comes and impacts the spring. Okay, so here is my strategy for all these problems. So I'm just going to draw it 2 times here, so bear with me for a minute. So here is one situation, and I'm just going to copy this and use it in the next situation as well. So here is the wall and so on. Okay, and here was the box, which I'm going to draw in a minute. Okay, so here is a box that was traveling. Okay, so this is the position 1. Okay, so let me call this as position 1 here. Okay, so this is the box at position 1. Then what else did I have? I had the spring element, right? So I'm going to just copy that from here, okay, because I don't want to do any extra work. Okay, so I'm just going to copy that, and I'm going to bring that guy here. Okay, so this is the spring element here. Now we got to be a little careful. Okay, so I want to make sure that these distances and all are marked very carefully. Okay, look at this. Now this distance here, okay, starting from the end of the incline all the way to where the spring is present, is going to be, if the total unstretched length of the spring at this position is L naught. Okay, so if this distance is L naught, right, that's what we know from the beginning of the problem. Okay, and we know that the total length of the horizontal portion is 3 meters, which means that this distance here is going to be 3 minus L naught. So many meters. Okay, so this is the box at position 1. Okay, this is and at position 1 the box has a certain velocity, so I can write that velocity here. Okay, so v1 is going to be 1.12 meters per second, and in this problem I'm going to assume a line which is my datum. Okay, so my datum is going to be a horizontal line, and it's going to be the same horizontal line for any position, whether I'm looking at position 1 or position 2. So this is going to be called my datum, and so at position 1 I'm going to measure the height of this box from the datum. Okay, so which means that I'm going to draw these, and I need some dotted lines here, so please bear with me. That's going to be a dotted line, and then this is also going to be a dotted line here. Okay, and then I need one more line which I'm going to draw from the box whose dimensions are negligible, because we are treating the box as a particle. Okay, so starting from here to there, I know that this angle here is 30 degrees, right, which means that this height I'm going to call it as h1. Okay, and h1 can be easily found out as 33 times sine 30, because this distance here is 3 meters. Okay, so that's known to us as 3 meters. Okay, and this is also going to be a dotted line here. Okay, all right, so this is the situation here. Then I'm going to take this and then draw the same thing right side on its side. Okay, so I'm just going to maybe copy some of these things. I guess in the process of copying I'm maybe moving them and so on. I don't want to do that, so I'm going to copy that and I'm going to paste it here. Okay, so that's my incline. I can get rid of this guy. I've already taken care of it. And then I have a horizontal portion on my incline. Let me make sure that that is drawn here as the darker colored portion here. Okay, I'm going to copy that and I'm going to paste that here. Okay, now watch what's going to happen. Okay, I had this wall here. Okay, so I need to draw that as well. So that is the situation here. Now this is the box at position 1, and I'm going to call the next position as position 3. Okay, so first of all, where is the box now and where is the spring now? Because the box has impacted the spring is now going to be compressed, as you can very well imagine, right? So which means that if I take this piece of the spring, I'm going to take that piece will have the same length, but the rest of the spring would have compressed. Okay, so if I maybe draw it now, it's going to be the following manner. So this is going to be a little smaller than what it was before. Okay, as you can very well imagine, which means that now if I call the length of the spring as some L1, let's say. Okay, so now I'm going to call the length of the spring as L1. Okay, let me draw this as a straight line. Straight lines, as I have found out, are my bane. Okay, I don't know, for some reason this software doesn't like me when I try to draw straight lines. Alright, so I'm going to call this length as L1. This is L1, so this is the length of the spring when it is compressed to its maximum position, as you can very well imagine. And so here is what I'm going to say. Okay, what is the total length now, and where is the box? The box, if I copy this box and if I paste it, I guess I have to draw it as a, well, you see, so now I made the mistake of not drawing it horizontal, right? So this box is going to be sitting, that's a circle that suddenly became a circle. Okay, now it's a box. Okay, it was a little thinner to begin with, right? So let's see. Okay, so let's imagine that this is the box that we're talking about. Okay, so this box is now sitting here, and then it has impacted the spring. Okay, so you see that the spring has compressed by a certain amount. Okay, I'm going to say that the maximum compression of the spring is x maximum. Okay, so say, I'm going to write that here. So say the maximum compression of the spring at position 3, okay, which is this position here. So I'm going to call this as a position 3, okay, is x max. Okay, which means that the total length now in this direction is going to be the following. Okay, so in the horizontal direction, the total length is going to be starting from here, okay, all the way up to here. What is that length going to be? Okay, so that length is going to be 3 minus L naught plus x maximum. Okay, so that was an initial length, but now you see that the spring is compressed by a certain amount of x max, which means that obviously that extra distance is now available to me when I come to this particular position. My datum remains the same as before. Here is my particle at position 3. Okay, so this is position 1, position 3. This is the box or the particle at position 1. And likewise, I'm just going to label that right out here and say this is the box at position 3. I hope this makes sense to everybody. Okay, so this is box at position 3. This is box at position 1. Okay, and it is quite obvious to see that at position 3 the box is at the datum itself, right? Which means that if I'm looking at potential energy and so on, then it's going to be 0. And the other nice thing here is this. Okay, when the spring is compressed to its maximum, the box at that instant has a velocity which is 0, because the box is probably going to start turning back because it's going to be compressed and the spring is going to start pushing it back if the spring is not that stiff, right? So that's also something that we can say. Okay, so at maximum compression of spring, the velocity of the box is equal to 0. Okay, so which means that, if I go back to my figure here, I can say that the velocity at position 3 is going to be 0 meters per second. Okay, so this is still the same spring, the same stiffness. The stiffness does not change. It's a material property, right? It is just that the length of the spring is now different. Okay, and x max is the amount by which this spring has deflected. Okay, that's essentially what we are saying here. And if you want to think of it this way, x max is going to be the difference between L0 and L1, essentially. Okay, so maybe one equation that we can write out here is the following, that L1 is going to be L0 minus x max. Okay, all right. So here is what we have, and a couple of things that we can note down here. First of all, we know that there is amount of friction that is going on. So this is going to be mu k of 0.15, and on this surface this is mu k of 0.3, right? 0.3 likewise. Okay, so using these two figures, I'm going to start writing out my energy terms. But before that, we will just make sure that we have everything accounted for. So at position 1, the box has an initial velocity. It's going to travel down this ramp here, and then it's going to come and hit the spring. As it hits the spring gets compressed, which is now position 3, and we see, and I call this as position 2, which we are not really interested in that position, so I just want to write it out anyway. So this point here on the box is there, I call it as position 2. Likewise, that is also position 2, which is the point where the incline becomes horizontal. Okay, and this was position 1. Let me label that again on this figure as well. Okay, and then this spring compresses, and we need to find out, okay, what is the maximum compression of this spring using work energy principles. Okay, so let us look at it. Okay, so at position 1, okay, what are the things that we have? Okay, first of all, at position 1, the velocity is known to us as 1.12 meters per second, which means that I know that this box is going to have a certain kinetic energy at position 1, so half m v1 square. Okay, so this is going to be the kinetic energy at position 1. Then I look at potential energy. Okay, so there are two things, right? When you look at potential energy, there is potential energy due to gravity at position 1. Okay, now the important thing is this: if, let me go back to my figure here, if the box is above the datum, this potential energy is going to be positive. Okay, so something to note here. So potential energy due to gravity is positive if the height of the particle is above the datum. Okay, otherwise it's negative. Okay, if the height is below the datum, then potential energy due to gravity or that height will be negative, will be minus mgh. Okay, so if the height is above the datum, potential energy is positive. So let me maybe write it this way here. So this is just a general statement. Okay, so if it is above here, then the height is I was thinking of writing it as negative, but it's almost like then h has to be negative. Okay, so PEG is plus mgh if h is above datum, and PEG is minus mgh if h is below datum, and we choose the datum. Okay, so datum is our choice. Okay, but the important thing is if you choose a datum at the beginning of the problem, you have to maintain it to be the same for any position. Okay, so that's also something I want to write down here. So datum, if we choose a datum to begin with, it has to be the same throughout the problem. Okay, I hope this makes sense. Okay, so with all these said, so potential energy due to gravity is positive if the height of the particle is above the datum. If the height is below, then h is negative. H has to be negative, so this is plus or minus mgh. So for our situation, if I go back here and look at it, this height h1 is a positive height. Okay, so this is going to be mgh1, and you can see that h1 is 3 times sine 30 here. Okay, so I can also write that here. So h1 is 3 times sine 30, so many meters. Okay, so I come here, PEG1 is plus mgh1. Then I also look at the potential energy due to the spring at position 1, and I see that at position 1, let me make these a little above here so that they are all in line. At position 1, the spring is unstretched, so this is equal to 0. Okay, this is 0 because because the spring is unstretched at position 1. I mean, there is no spring at position 1, first of all, to begin it. So maybe let us write it that way. Okay, so because the spring is not of any concern at position 1. Okay, so this is because the spring is not of concern at position 1, and also it is unstretched at position 1. Okay, and also spring is unstretched at position 1. Okay, so these are the reasons for why this is not going to be an issue for us at position 1. Okay, so three things that you want to look at: kinetic energy at position 1, potential energy due to gravity, potential energy due to spring. Okay, then I go to position 2. Okay, so then I look at position 2, so at position 3, I'm sorry. Okay, so we call this at position 1, and let me go here, follow the same procedure. Okay, at position 3, first of all, I know that velocity is 0, which means that the kinetic energy at position 3 is 0. Okay, then I can also write the following. Okay, I can say that potential energy due to gravity at position 3. Look at this. If I go to position 3, right, the height from the datum is inconsequential because this is a particle, so h3 is actually 0. Okay, in this case there is no height from the datum. Okay, so which means that at position 3 the particle has 0 potential energy. So at position 3 this is going to be 0. Okay, so particle is at datum. Okay, and then the spring, don't forget the spring. Potential energy of the spring at position 3 is going to be half times k times, since it is deflected by an amount x max, then this is going to be half x maximum square. Okay, so these are the things at position 3. Then I write the work energy theorem. Okay, so general form of the work energy theorem. General form of the work energy theorem. Between positions 1 and 3. Okay, so here is the idea. So U1, 3, others, plus PE G1, PE S1, KE1 is equal to PE G3, PE S3, KE3. Okay, so this is the situation that we have. And then I know that the potential energy due to spring at position 1 is 0, and potential energy due to gravity and kinetic energy at position 3 is 0. So I can get rid of some of these terms for me. So this is gone, and then this is gone. The big thing is this guy here. Okay, this is U13. This is due to friction, right? I guess something is going on here that doesn't make any sense to me. Okay, so this is due to friction. I just wanted to draw an under brace, and I got to run through so many hoops. Okay, so this is going to be the work done by the force of friction against the motion of the particle. Okay, so this is the only other force that we have here. We don't have any other applied forces. Okay, so we do not have any other applied forces. Okay, so the only work done that is to be considered in the others term is this work done due to the force of friction. So here is an important thing that we got to consider. Okay, so let me look at my inclined surface again. Okay, so let me draw two things. Okay, the first thing is at any point between position 1 and position 2. Okay, then I'm having one position 2 and then position 3. So here is the basic idea. because the particle is traveling from 1 to 2 and then from 2 to 3, I have to take care of the fact that, okay, u13 others is equal to u12 due to the friction force plus u23 due to that friction force between 2 and 3. Okay, so this is essentially going to be, if I write it as an integral, this is going to be integral because friction is going to do work against the motion of the particle. Okay, so this is going to be a negative quantity. Okay, so this is going to be f mu k between position 1 and position 2 ds minus integral from position 2 to position 3 f mu k ds. Okay, so the negative sign here, okay, the negative sign here, because friction opposes the motion direction. Okay, so that's something that you want to keep in mind. Now, how do I find out this f mu k between position 1 and 2 and position 2 and 3 is I draw a free body diagram. Okay, so the first thing is I draw a free body diagram here. Okay, so here is the particle. What is the force acting on this particle? Here are the forces acting. Okay, so the particle is trying to travel from 2 to 3, so there is going to be the weight of the particle, which is m times g. Then there is a normal force here. Okay, so I'm going to call this as n23. Okay, the particle is accelerating, right? And so if it is traveling to the right, this friction force is going to be pointing to the left. Okay, so this is going to be f mu k between 2 and 3, which means that I have to do a qualification here and say, okay, this is going to be f mu k. Let me write this ds a little away. Okay, so this is going to be f mu k between 2 and 3. Okay, and likewise this is going to be f mu k between 1 and 2. Okay, between 1 and 2, and I'll be rewriting this, so there is not any issue. Okay, then I got to draw one more figure here, which is the particle at some point, on its travel from 1 to 2. Look at the forces acting on it. The weight of the particle is always going to be acting vertically down. Okay, so this is going to be mg. There is no doubt about it. Okay, then the normal force is going to be perpendicular to the direction of the incline. Okay, so that's going to be n12. The particle is trying to travel down, which means that the force of friction is going to be acting up the incline. So this is going to be f mu k 12. Okay, I hope this makes sense. And we are going to say that, okay, if I'm doing this from the free body diagram and so on, I can say the following. So now look at this mg here. I can break mg into components, okay, along the direction of the incline and perpendicular to the incline. Let me maybe very quickly do that. Okay, so there is one component, and this is going to be 30 degrees. Okay, so this angle here is going to be 30 degrees because of the fact that the incline is at 30 degrees to the horizontal here. And this is going to be mg times cosine 30, and of course I'm going to have this mg times a sine 30 component, which I'm not too worried about. Okay, so from general force balance I can find out the following. Okay, so n12 will end up being equal to mg times cosine 30. Okay, and then I can also see that n23 is going to end up being just mg. Okay, this is from force balance on the particle. Okay, and so what am I going to do with all this information? So here is what I'm going to do. Okay, so I'm going to rewrite my work u13 others. So u13 others. Okay, this is going to be minus integral from f mu k from 1 to 2. So this is from position 1 to position 2 ds minus integral from position 2 to position 3 f mu k 23 ds. Okay, and then we know the following. We know that F mu k 1 to 2 is going to be mu k times n1 2. Okay, so this is going to be mu k, which is 0.15 in this case, right? So this is going to be 0.15 times mg times cosine 30, so many newtons. Okay, and then F mu k 2 to 3 is going to be that mu k n 2 3, okay, which is going to be 0.3 times mg, so many newtons. I just wrote that as newtons because I know that n is a normal force as well. Okay, so if I go back here, and that's what I have, n1 to n2 3, and I'm just going to start substituting. Okay, my limits of integration is going to be just the distance because I find that the friction is a constant force. Okay, so which essentially tells me that u1 3 others, this is going to be minus integral from 0 to 3 meters, because I'm traveling all the way from here to 1 to 2, which is a distance of 3 meters. Okay, distance from 2 to 3, you got to be careful there. Okay, so this is first of all going to be 0.15 times mg cosine 30 ds minus in distance. Okay, so this is where we got to be a little careful. When I'm doing it from 2 to 3, I'm starting off at position 2 as a 0. So this is a new path for the particle. And then this integral here is going to be, the limit here is going to be 3 minus L naught plus x max. Okay, and then this is going to be 0.3 times mg times ds. Okay, so watch out for these limits of integration. Okay, and if I look at it, then u1 3 others will end up being minus 3 times 0.15 times mg cosine 30. Okay, that's a 3 there, minus 3 minus L naught plus x max times 0.3 times mg. Okay, so this is u1 3 others. Okay, so be careful when you're doing the limits of integration. That's the only place where things can go wrong in this problem. Okay, and so I go back and bring my expression from above, which is the work energy expression here. So this is what we had simplified it to, right? So we had all of this here. We found out that potential energy, kinetic energy in certain situations are not going to be of any use to us. So here is the situation, and let me bring it to this page and get rid of that guy. Okay, and let me bring that down here. Okay, so now we have everything. Okay, so I'm just going to start filling in the details, and then we will go to the end of this problem. Okay, all right, so u1 3 others, which is going to be minus 3 times 0.15. The mass of this was 2, g was 9.8 times cosine 30 minus 3 minus L naught, which was I think 0.8, plus x max, which is something that I need to find out. Okay, and I still have a few more things to write down here, times 0.3 times the mass, which was 2, times 9.8. Okay, so this was u1 3 others. So I'm just going to put a big bracket right down here. Okay, and then I'm going to say PE due to G1. Okay, so that's going to be plus potential energy due to gravity at position 1. This was going to be mass 2 times 9.8 times 3 times sine 30. Okay, so that's what we had here. And kinetic energy at position 1 was half times the mass times the velocity square. Okay, so bracket close. This is equal to stuff on the other side. Okay, so that's going to be potential energy due to the spring, which is half times k times x max square, and kinetic energy can also be knocked out here, which I did not. I thought I had it done there. So let me also go back and do it here. So this kinetic energy is also gone. Okay, because it's 0. And that's about the only thing I have on this side here. Okay, the stiffness of the spring is known to me as 20, so let me substitute that here instead of this guy here. So that's going to be 2 times 20 times x max square. Okay, so this is stuff on the right hand side, and eventually what will happen is that, okay, after simplification, okay, I'll end up getting the following. It will be a quadratic, so we will end up with a quadratic in x max. Okay, and here is the quadratic. Okay, so after simplification, this is what I'm getting. Okay, we are almost at the end of this problem. That's a feeling of relief, but you know, we just got started with solving some of these problems, so you're going to see a little more nicer problems as we continue to do this. Okay, so x max square, and then I'm going to have some 5.88 x max minus 10 is equal to 0, and then I get the roots from this, so I solve for x max. Okay, so solve, and I get x max is equal to 0.74 meters. Okay, this is the only useful root that comes out of that quadratic equation. The other root is going to be discarded. Okay, so once I solve for x max, then this is the maximum compression of the spring. Compression of the spring. Okay, and then the length of the spring, L1, which was given to us as L0 minus x max, is going to be 0.06 meters. This is the length of the spring at the maximum compression. Okay, so that was also something that we were supposed to find out in this particular problem. Okay, so very quickly, let me go back and then rephrase what is going on in this problem. Okay, so we have a box. This box is starting its travel down the ramp from position 1, travels all the way to position 2, hits the spring at this position, which I'm calling as position 3. What am I supposed to do? This ramp is a rough surface. This horizontal surface is also a rough surface. So if there is a roughness, then the friction force is trying to slow down the box. But then the box is also gaining kinetic energy because it is falling from a height, right? So there is an increase in its energy. There's a trade-off taking place. Okay, it's losing velocity, but at the same time gaining energy by trading off from the height. But we have to include the factor of friction as well in this particular situation. Okay, so how do I find out the maximum compression of the spring? Here is what I do. I draw two positions. Okay, so here is position 1, here is position 2. In position 1, the box is at the top of the incline. Position 3, the box has impacted the spring. At the maximum compression, the velocity of the box is 0. So I write down the kinetic energy at position 1, potential energy at position 1, kinetic energy at position 2, and potential energy at position 3. 3. So it should be 3, not 2. I don't know why I keep saying 2. Okay. Then here is something that I just wrote down as well. When you're looking at gravity, be careful. If the height is above the datum, then it's a positive potential energy. If it's below, it's a negative potential energy. Who chooses the datum? You choose the datum. But if you choose a datum to begin with, you maintain that to be the same throughout the rest of the problem. Okay, so you do not just change the datum willy-nilly. Okay, that's at position 1. We have all these terms. Position 2, write down all the energy terms. Then make sure that you're accounting for any other forces. We have a force of friction which is trying to do work against the motion of the particle, so that's going to be a negative force. Okay, or a negative work done, so this implies that I have to draw the free body diagram at some arbitrary position between 1 and 2 and between 2 and 3. Okay, so these are the free body diagrams at some position between 1 and 2 and between 2 and 3. Okay, I'm not drawing the kinetic diagram because I'm not using the F is equal to mass times acceleration equations. All I need here is, okay, what is the friction force? That is why I'm drawing the free body diagrams. Otherwise, I don't even need this. If there is no friction force, I just go on my merry way without drawing any of these nonsense. Okay. Then I come and say, okay, U1, 3 others is the sum of the friction work done from 1 to 2 and then from 2 to 3. But then the friction work is negative because it is trying to resist the motion of the particle. So you got to put the negative sign here. Okay, then once you do this, you just go back to your work energy equation, make sure you cancel off all the terms that are zeros, and then substitute, solve for x max, you get a quadratic. Once you get a quadratic, you can find out the length of the spring at its maximum compression. I hope you enjoyed this problem. I will come back with more. All right, take care of yourselves. Bye bye.